Today we want to take a look at things that we are calling the fundamental theorems of calculus. Starts off in Calc 1, and we get just the one fundamental theorem of calculus, and then depending on where you go in Calc 1, another fundamental theorem of calculus called the second fundamental theorem of calculus shows up. They're really two parts of one theorem. We want to think about them as two parts of one theorem. What we need here is a continuous function on a closed interval and some value from that interval. Only need that for the second part. And the fundamental theorems of calculus says that the integral from a to b of f prime of x dx is f of b minus f of a. Another way to do this is to say the integral of f of x is capital F of b minus capital F of a, where capital F is an antiderivative. So this also makes an appearance. This is my shorthand for the fundamental theorem of calculus. So we also like to see this as the integral from a to b of f of x to x is capital F at b minus capital F at a, where capital F is an antiderivative of f of x. This would be a better way to say it because I stated that f is continuous on the interval from a to b. I did not require that f have a derivative. But this is the way we're going to think about it. And that's the one I wrote first, even though I wanted to switch the positions of these two lines. In the first part of the fundamental theorem of calculus, it says we can use an antiderivative to calculate a definite integral. That's the big idea here. Use an antiderivative to calculate a definite integral. In the first part, we learned that we can use an antiderivative to calculate a definite integral. The second part of the fundamental theorem of calculus says almost the same, but in reverse. The second part of the fundamental theorem of calculus tells us that we can construct an antiderivative with a definite integral. So the second part of the fundamental theorem of calculus says you can construct an antiderivative using a definite integral. So we can use an antiderivative to calculate a definite integral. We can use a definite integral to construct an antiderivative. It's kind of an if and only if type of setup. If A, then B, and also if B, then A. The second part is really important, that we can construct the antiderivative of any continuous function using a definite integral, because we know that we can calculate definite integral with area. That's the big deal here. We can approximate a definite integral with area. That means we can construct antiderivatives pretty much with multiplication. And moreover, we can do this, if we have enough information, we can do this to any degree of accuracy that we like. So that's a big deal. It's also important because not all functions have nice antiderivatives. That's the more important part about this. We can construct an antiderivative using a definite integral, This is good news because we can use, we can approximate any definite integral with just area. And it's important to be able to do this because not all functions have nice antiderivatives. So moreover, this is important since not all functions have a nice antiderivative. This is an important thing to be able to do because not all functions have a nice antiderivative. By nice antiderivative, I mean finite combination of elementary functions. So to construct an antiderivative, we might have to construct an antiderivative because the antiderivative either is an infinite combination of elementary functions, like a power series, or a finite combination of non-elementary functions. All the functions that we've named so far, any function that we've identified in your mathematical career that has a name, trig functions, radical functions, rational functions, exponential, logarithmic, those are all elementary functions. Even the weird ones like hyperbolic trig functions. Those are all elementary functions. Functions that have, the functions that are constructed, like using a definite integral, are not always elementary functions. So we could find an antiderivative, we can construct an antiderivative of e to the minus x squared, and that with the definite integral, and that would not be an elementary function. Or we can use an infinite number of terms. Take the power series for e to the x, drop in a negative x squared, and you'll have an infinite combination of elementary functions. But you can't have both for all functions. Good question. So this is just a reminder of our fundamental theorem of calculus, the relationship between antiderivatives and definite integrals. That is an important relationship. And a quick summary of why we think this is important. The first line that we wrote up here, where I wrote it with the derivative, which was pretty improper, but I'm pretty sure that the math cops are not monitoring my YouTube channel, so I'm safe. You don't want to mess with the math cops play hardball. Ever tried dividing by zero? Yeah, as an adult, yeah. They let you go with the warning when you're a kid. But if you're like an adult, like if you're in college, hanging out with your friends, getting drunk on Bud Lights, start dividing by zero, the math cops will show up and ruin your day. And they say that stuff goes on your permanent record. I'd like someone to tell me how I did in math in the 4th grade. I bet no one can, because I don't think this permanent record thing exists. I suppose my transcripts, but those only go as far back as like 1989, right? When I started school, started college. And honestly, at my age, if I needed my transcripts for like for whatever reason, I'm just going to end that relationship right there. Like if I'm like applying for a job and I go, oh, send us your transcripts. I'm like, oh, no, that won't be necessary. I go, but we can't hire you if you don't send us your transcripts. I go, yeah, I'm not going to, anybody that wants to see my transcripts at my age, you clearly don't know what you're doing and I don't want to be involved in whatever endeavor this is. You know what I mean? Anyway, what are we talking about? Oh, yes, the fundamental theorem of calculus, the fundamental theorems of calculus. What we see here is a structure that we want to think about generalizing. I think I only circled that in highlighter because I found out where I had put my highlighting erasable pen. We want to look at this structure. We're trying to integrate a derivative, and that means evaluating a function at the endpoints. Or we can think of it evaluate an integral by evaluating the function. I really messed myself up writing it this way. Laziness strikes again. We're going to evaluate this definite integral by evaluating the antiderivative at the endpoints. So we evaluate the definite integral by evaluating the antiderivative at the endpoints. Our general picture is that we're going to think of evaluating a definite integral by evaluating the antiderivative at the boundary. In this case, it's the endpoints. Said endpoints are there. I'm switching back and forth. So we're evaluating the definite integral by evaluating the antiderivative at the endpoints of the interval. The structure here is that we integrate something by evaluating some kind of antiderivative at the endpoint or at the boundary. And now is when I'm supposed to write the derivative one. So if we're trying to evaluate a definite integral of a derivative, we evaluate the function at the boundary. Important thing is that the thing in the integral is some kind of derivative of the function. We see a similar structure when we get to the fundamental theorem of calculus for line integrals. So the fundamental theorem of calculus for line integrals says find a vector field or start with a vector field and some path. If F is a vector field and C is a path from point P to point Q, I thought I had caught up after. Thought I had recovered from this time change. I clearly have not. So what I need is a on-off switch. So when stuff like this is happening, I can just shut off and shut back on again. I don't even need the vector field. I need a gradient field. At least I got the statement of the fundamental theorem of calculus for line integrals, this part sorted out. So the way we want to view this is we want to compare this with our original fundamental theorem of calculus, where we have the integral from a to b of f prime dx is f at b minus f at a. So we start off with just some interval from a to b. So here we have the interval from a to b. And since it's just an interval on the real number line, there's not much to describe. Start at a, end at b. What's going on in our fundamental theorem of calculus for line integrals is that we've taken this integral and we vectorized it. We made it some path in R2 or R3, starting at point P and ending at point Q. It's still one-dimensional, like our interval. Or our interval only has scalar information, all the real numbers from A to B. The path is going to be some curve, but still only a one-dimensional thing. So P and Q are the endpoints of this weird curvy interval. So that's one comparison. F at B minus F at A, that's just looking at the antiderivative at the endpoints. F at Q minus F at P, that's looking at the change in the antiderivative at the endpoints. The other piece we want to look at is the relationship between the thing that we're integrating and where we're evaluating. So in here, I've got f prime, I've got the derivative of this function, f. The gradient is acting like a derivative. It's a vector made up of partial derivatives of our function. In the case of the original fundamental theorem of calculus, that is the derivative. That's the derivative, and we're integrating the derivative from A to B. We can think of the gradient as being the derivative of the potential function f. I want to think of the gradient as the derivative of f. It's some combination of our partial derivatives. So you can think of it as a derivative, even though it's not really a derivative. Any questions? So we're evaluating the line integral by evaluating of a gradient field by evaluating the potential function at the boundary of the curve, at the endpoints of the path. Just like we integrated a derivative by evaluating the function at the endpoints of the interval. Any questions? It's not perfect. It is not correct to call the gradient of f the derivative of f, but it's acting in that capacity as far as how we set up our fundamental theorem. Any questions? All right. So there are other fundamental theorems that follow this same kind of structure. We want to integrate by evaluating some kind of antiderivative at the endpoints or some antiderivative at the boundary. Let's just write them down. Even though it is way too early to do this. So pause for copying. Write down this bunch of symbols. We don't know what everything means. And then we're going to think about what this must mean. So the integral over S of the curl of f dot dA is equal to the integral over C of f dot dr. Over on the right side, we see a line integral. That's just a regular old line integral. This is something that we want to label as a fundamental theorem of calculus. So let's talk about the relationships between certain things. The first one is an integral over S of something dot dA. And the second one is the integral over C of something dot dr. So on the left side, S is some surface over which we're integrating. So S is some surface over which we are integrating. S is some surface over which we are integrating. C is the boundary of the surface S. C is the boundary of the surface S. By pointing out this relationship, we're trying to connect this fundamental theorem of calculus of all these things, and we don't know anything about them, but we're trying to connect this to our previous fundamental theorems of calculus to show that this fits that description. The big idea is I want to integrate some derivative by evaluating a function at a boundary. So if we integrate over this surface, this dot dA reinforces the surfaceness of this. It's an area. It's two-dimensional. And C is our boundary, which is a curve, and it's one-dimensional. Emphasized by this dot dr. We're integrating this curl function, whatever that might be, dot dA over some surface, and that's the same as the line integral of the vector field F evaluated on the boundary of that surface. Just like we find an antiderivative and plug in the endpoints. That's the boundary of the interval. What this means is that the curl of F is in some way a derivative of this vector field, but it's clearly a vector. Curl of F is involved in the dot product. So it's a vector and some kind of derivative of F. We don't know what curl of F is. I don't know why I started shouting halfway through that. Calm down, man. Right now, we don't know what the curl of F is. Here are some things that we do know. It's involved in a dot product, so it must be a vector. It's a vector. It must be a vector because it's involved in a dot product. And the other thing we must know, it's some kind of derivative of this vector field F because it's taking that position in the fundamental theorem of calculus. We could think of it as some kind of derivative of a vector field because of its position in the fundamental theorem of calculus. Integral over the integral over I of some function dx is the antiderivative at the endpoints of the integral. So I got surface, we've got boundary, we got derivative, we got function. So this curl of F is some vector derivative of this vector field. We don't know how to calculate it. We don't know what it can be used to represent, but it's some kind of vector. other suppositions that we can make. I've got this dA, which is some small piece of a surface, and it's a vector. So this dot dA just thinking ahead, thinking about what these things could mean, let's try to take in all the information that we can get from this, a collection of symbols that we know nothing about. But their position in this theorem should allow us to piece some things together. This vector dot dA, or this vector dA, it's a vector, it's involved in the dot product. And because of its position in the fundamental theorem, it's some small piece of the surface S. It's some small piece of S, but it's also a vector. So if we've got a surface and we've got a vector representing a part of that surface, we need to think about how that vector is going to be represented, how that vector is going to represent that piece of surface. Since a surface is a two-dimensional thing and a vector is a one-dimensional thing, we have to guess about what dA represents. So that raises the question, how is dA related to S? What's this vector doing representing some small piece of the surface? Surfaces should be a piece of area, not some vector. What's this dA going to have to do with S? Any questions? Here's Stokes Theorem. Raises some questions, but the idea was not to define what these things were so that we could understand everything right away. The idea was to see the structure that's going on. Stokes theorem is cool, got named after a person. The other one is divergence. We're going to do a similar exercise with the divergence theorem. We're just going to write down what it is, and then we're going to think about what all this stuff must mean. We're going to think about the structure of the fundamental theorem of calculus. So the divergence theorem says that the integral over W of the divergence of f dv is equal to the integral over S of f dot dA. Over on the right side, we have a surface integral. We're not really clever in our naming of things. Integrate over a line, it's a line integral. Integrate over a surface, it's a surface integral. Let's go through the same procedure on all the other parts. W is some solid. W is the solid over which we are integrating It's a solid and it's three-dimensional. Over on the other side, I've got an integral over S dot dA. This is a surface area. We're integrating over a surface. S is some surface that's related to W. S is the surface of the solid W. W is going to be the entire orange. S is the orange peel. So we're integrating over some solid by looking at an integral by evaluating over the boundary of that solid, which is going to be a surface. Once again, we've got this function in that we've introduced. I haven't even introduced, I've just written it down. Ever like taking a character from the background and suddenly making him a character in the next movie? Like, oh, see, we introduced this character before. It's like, oh, no, that person was just sitting in the background and you happen to bring them back. But based on how things are written here, oh, the other thing that supports our volume thing, dV must be some piece of this solid W, and dA, well, we still need to know how dA is related to the surface S, because dA is some vector. Note that dV is not a vector. We wrote the divergence of the vector field F, and we just multiplied it by dV, not a dot product. So here are some things that we know about this div F. So this div F, once again, we don't know what divergence of F is. But based on how it's represented here, there are some things that we can see about it. First, there are things that we do know. It's a scalar. It's not involved in a dot product or a cross product. It's being multiplied by this volume dV. So it's a scalar. It's just involved in multiplication by dV, which is also a scalar. If it had an arrow, then it'd be a vector. This would stop making sense. I don't know if it makes sense now, but. It's some kind of derivative of the vector field F. Based on its role or position in some fundamental theorem of calculus. So apparently, these vector fields have two different kinds of derivatives. Some kind of scalar derivative and some kind of vector derivative. This is not surprising, because integration is just multiplication, but one of the factors is variable. When we have vectors running around, we've got two kinds of multiplication. scalar multiplication and vector multiplication, dot product and cross product. So we shouldn't be surprised that two kinds of multiplications are going to be involved here. Two kinds of derivatives are going to show up. The analogies aren't perfect, but integrating over a boundary, integrating by evaluating over a boundary. That's the common thread that we see in all of these fundamental theorems. That's like one of the things about fundamental theorems. We do need to talk about what a surface integral is. We need to talk about what curl is and what divergence is. But before we do all that, we need to understand how integration works and how we construct things called fundamental theorems. There's a lot of fundamental theorems. The first one you usually run into is the fundamental theorem of calculus, the first one you run into and name. But at this point in your career, you've also heard of the fundamental theorem of algebra and the fundamental theorem of arithmetic. You probably haven't heard them called these things. Anybody heard the fundamental theorem of algebra? You do know it. Fundamental theorem of algebra is just you can factor polynomial. That's pretty much it. An nth degree polynomial has n factor, or n zeros is one way to say it. An nth degree polynomial has n complex zeros. I mean, you can factor over complex. There's also a fundamental theorem of algebra, which you also know, but maybe not have heard, because the time you learned it, it'll be ridiculous to be like, oh, this is the fundamental theorem of algebra, children. And that's just, or sorry, fundamental theorem of arithmetic, children. You're too young to hear words like that. Swearing, no problem. Fundamental theorem of arithmetic, no. Not okay. I need one of those little things up here that says language. But that just means we can factor numbers. There's a unique prime factorization. There's more to it than that, but these are concepts that you're familiar with. You hear them call those things. Math has fundamental theorems running all over the place. There's fundamental theorem of finitely generated abelian groups, all kinds of weird shit. But these are the fundamental theorems of calculus. These are the important things to take away, the similarities in all these calculations. Any questions? We are going to get into some examples of what some vector fields, what some line integrals might mean. And then we'll get some examples of what surface integrals might represent. But more important, this being a math class, is not the physics that we're going to pilfer to use as examples, but the big idea about what integration is and all of its forms. Any questions? I know I should do more engineering and physics examples, but I am neither an engineer nor a physicist. And math is not the servant of the sciences. Math is the queen of the sciences. So everything else needs bow down. Math doesn't serve the other subjects. The other subjects just rely on math. All right, that's going to be it for today. I will see y'all on tomorrow. Have a good day and thanks for playing.